Good afternoon. Yes, you're still alive and kicking. Okay, I really thank you for staying around and listening to my talk. This is a case study also. We just started our research on 3D printing, and I just want you to feel what are the challenges in research on 3D printing, particularly on materials development. So the title is 3D printing of NANOCOMPOSITES, ITDI experience. Okay, so this is the outline. I will give a short introduction. I will mention the nanomaterials that we use for additive manufacturing. And then I will discuss our study on developing nanocomposites, the fabrication of nanocomposites, and challenges that we encountered, and what would be our future R&D. Okay, let me introduce our institute. ITDI is one of the research institute under the Department of Science and Technology, and it conducts multidisciplinary industrial research and development, provides technical services, and knowledge translation or technology transfer and commercialization. And it also harnesses know-how in new technology, such as additive manufacturing technology, and of course, including product innovation. So there are 5 research divisions in ITDI, and one of them is the Material Science Division, wherein I am the chief of that division. And these are the following areas that we are working on. Aside from additive manufacturing, we develop green technologies for industrial applications. We develop polymeric membrane technologies using local materials. And right now, we're working on nanofibrous scaffolds for tissue engineering, wherein we are also going to use 3D printing because we're developing stem cells for cancer growth. And we are also working on quantum dots using green technologies, also on natural fiber composites for engineering application. And we are also into advanced ceramics for industrial application, nano coatings for manufacturing industries, and lastly, we are spearheading nano safety because there are a lot of work, exposure on nanomaterials, and there are nano-enabled products that we are already using in the country. So we are spearheading the nano safety, particularly on laboratory protocols and policy formation. Okay, so under the program on advanced additive manufacturing, I had mentioned yesterday that we have 2 projects. So one of which is the development of multiple materials platform for additive manufacturing with the acronym MATDEM. So right now we are working on advanced ceramic materials, and these are some of the products that we have already conducted or completed using subtractive manufacturing. So we have electronic ceramics. We have developed bioceramics. This is a porous material wherein we have tried to implant this to humans already a couple of years ago. And we also developed silicon carbide based products, and of course industrial ceramics like ratchet rings. But with the advent of 3D printing, which is a revolutionary in the making, we are now going to translate these subtractive products to additive manufacturing. And right now, there are commercially available materials used in 3D printing. And this has been discussed enormously this morning, and there are a lot of samples available also in the exhibit area. But we would like to localize these products. Because as you know, imported products which are available are expensive. In additive manufacturing, there are a lot of challenges. So if you work on materials, you have to consider these challenges. One of the biggest challenges is the widespread adoption of additive manufacturing is also the supply of materials, for example, polymers, metals, and ceramics that can be used to fabricate the items. And every year, new materials are advanced in additive, resulting in better microstructures and enhanced material tolerability. So even if the product that you develop using the additive manufacturing should have a good packing density and a good powder flow during manufacturing. So these are some of the properties that you need to consider. And there are also, and material properties has something to do with the design constraints. Like, for example, the high dimensional accuracy, the whole components to get a fine structure, and when you develop products, it must have a smooth surface finish and should be dimensionally stable under tensile load, and it should have a strain rate, and you should also consider the temperature of 3D printing. Right now, there are nanomaterial additive. Nanomaterials as additive for 3D printing. Yesterday, it was mentioned that it is possible, there has been a lot of work already on using nanomaterial as additive in 3D printing. So in our laboratory, we have these various nanomaterials that could be used for R&D in developing nanocomposites in 3D printing. So we have nanotitanium dioxide, nanocalcium carbonate, halocite, nanoclay. We have bentonite, nanosilver, nanosilica, nanozinc oxide, graphene, carbon nanotube, nanozeolite. So if you want to work with us, we have available nanomaterials in the lab. And we are also we have characterized all these materials, and these are some of the nanomaterials that we produce locally. So we have nanocalcium carbonate, nanoclay, halocite, and we also have silver nanoparticles. So these additives are used to produce nanocomposites. So I just want to share how we prepare nanocomposites. There are three methods in which we use to prepare this. We have the in situ polymerization, wherein the monomer molecules diffuse in between the layers. And we also use the intercalation of the polymer using the solution approach. And the most common technique is the melt intercalation technique. But take note, just mixing this material doesn't guarantee that you have produced nanocomposite. You have to test whether you have produced a monolithic structure. Meaning, if you have a monomer and you add a nanomaterial, if you produce this type of structure, you still produce a conventional composite, even though if your additive is a nanomaterial. The requirement is you should be able to produce these two types of structure, the delaminated structure or intercalated structure, to get a monolithic structure, and you can say that you have produced a nanocomposite. And there are tests that could guarantee the performance of your product using X-ray diffraction or TEM. Okay, so when we produce the nanocomposite, we prepare the master batch. So here we add nanomaterial to a polymer matrix. For example, in this case, we use LLDPE or linear low density polyethylene, and we added nanomaterial, at a concentration of 50%, and then we blend it and pelletize, blending using the twin screw extruder. And then the master batch is blended further into a virgin resin at various concentration. In this case, we use this extruder to produce the filament. So this is the filament for 3D printing. Okay? So further, there are conditions that you need to consider in 3D printing. You need to control or optimize the extrusion parameter of the extruder, as well as control the diameter to get a consistent diameter of the filament, okay, for 3D printing. Okay, so let's be working on the filaments. So we prepared 1 to 7% concentration of nanomaterial. In this case, we used the local nano-precipitated calcium carbonate. So we produce filaments for 3D printing. And, okay, so we also use modified nanozeolite as an additive to produce nanocomposites. And these were the different extruded filaments ready for 3D printing. But there are challenges in 3D printing. As you know, earlier it was discussed that 3D printing is easier when you use PLA, which is mostly used in 3D printing, polylactic acid, ABS, acrylonitrile styrene, right? Because they easily stick on the build plate. In our case, it's the first time that we use HDPE, high-density polyethylene, as the matrix for 3D printing. And we encountered this problem. Okay, so we use Gigabot 3. This is a type of printer wherein you can print large structures, 1 by 1 cubic meter of print. Okay, so this is an FDM, and we try to print our nanocomposite. So if you don't optimize the parameter, you can get this type of print. But when we try to operate the printer, we obtain this type of result. The print or the filament, the extruded filament did not stick on the metal build plate. So we were not successful in printing 7% nano-precipitated calcium carbonate nanocomposite in HDPE matrix. Okay, so since it did not stick on the build plate, we tried to use glue. So there were studies that you need a coating on the build plate for you to be able to print on the build plate and have your object stick on the build plate. So we use a common glue stick. But just the same, there was no print on the build plate. That was the first trial. Then we used the hairspray because we learned that hairspray or spraying a spray net on the build plate will help hold the sample. This is the strongest hairspray that we bought commercially, but still, initially it stuck on the plate, but when the spray dries, it detached on the build plate. Now we use advanced adhesive. We use the nanopolymer adhesive this time. So do you think because it is already nano against nano material, it will stick? Unfortunately, it still did not stick on the build plate. So what was the problem? The problem here, so these are the parameters we use. Next. The problem here is that the material, HDPE, has a high crystallinity and a high crystallization rate. Therefore, it has a high shrinkage. Okay? So, according to literature, there was very poor adhesion on the build plate using a material with very high crystallinity. Okay, so the solution is to use SEPs as a build plate. This is the styrene, ethylene, butylene, styrene. So we have to prepare a new build plate. So this is the SEPs build plate with this thickness. So we have to replace the build plate with a SEPs build plate for the polymer to adhere, or the material, the nanocomposite, to adhere on the build plate. So as I had mentioned before, the reason why we didn't get a good print is because the material has a massive shrinkage, right? Which caused voiding, warpage, and poor adhesion on the build plate. But before you can get good results, mind you, you still have to optimize the 3D printing parameters such as the temperature, the diameter of the nozzle, the extrusion rate, the build plate temperature, and getting the right build plate material. Okay, I just want to summarize our result. Using the build plate with no coating, there was no adhesion. Build plate with hairspray, no adhesion. Build plate with glue coating, no adhesion. SEPs, it has a good adhesion. Okay, so we still have to work more on this experiment. We can also try fabricating an HDPE build plate and try to roughen the surface of the same material, HDPE, and then try to print. But there is still a challenge here on how to remove the specimen on the build plate because it is the same material. But we could try this experiment, and also we could try higher loading of the additive. We could also try that. And you could try also using other nano additive. And also we could try using recycled HDPE or polypropylene with nano additive. And also we could try printing using other formats of 3D printing. If we use a powder material, then we could try SLS printer. And you could also try producing or fabricating nanocomposites with other polymeric matrix. So that's, if you would like to join MATDEP with our research, you're all welcome. We have nano additives, we have polymer matrices, and we have the AMCen Innovation Grant to support your research or your ideas. Okay, thank you so much.